I'm Kurt Busch, CEO and co-founder of Syntiant. Welcome to our video series, Edge AI Talks, where we discuss the trends and technologies that are shaping the future of artificial intelligence at the edge. I'm here with one of our co-founders, Dr. Steph Bailey. When we started, AI was really something that happened in the cloud. It was an NVIDIA thing. Tell us about your view of what's happened with Edge AI over the last almost decade.
When we started, that first year was, I think, the first year that NVIDIA put any deep learning specific electronics into their products. So they were on the train. For us, what we could see was that basically this dichotomy between two different pieces of the digital world. One's application, and that's heavily driven in the server world, and the other is interface, which is kind of what we focus on. And a lot of the interface stuff was pioneered on servers. So for example, speech recognition and things like that were run, at scale in services like Alexa's voice assistant. But really, those functions that are essentially taking, physical world phenomena and stuff like that and boiling it down into something applications can use, eventually belong in the terminal devices at the edge. Okay, and so when we started, I had no knowledge myself of what was happening in deep learning at the edge, and it was pretty nascent. But we could see, with our journey fairly quickly that type of segmentation in terms of the total architecture of the system is what will be inevitable and what was happening. And so we just started delivering, outcomes into devices that, that needed it, and that's accelerating.
There's about, I don't know, let's call it 24 billion small processors sold every year, MCUs, MPUs. And none of those can handle a rich AI workload.
Yes.
Or much of any AI workload for that matter, but let's just say a rich one.
Yes.
What makes the architectures that you and your team have developed that make it different to be able to handle those kind of AI workloads?
We basically started from scratch, focused only on running neural networks in these processors. And one of the things about these constrained devices, if you look at like NVIDIA on the server side, the fundamental constraint there is the memory bandwidth that goes off chip. Okay, and so what that gives you actually, or even a handset device, if you're running a large model that's coming out of, or a compute client out of DRAM, it's not as critical that the processor inside is as efficient in terms of area and power because of the dominant factor of the data movement off chip. When you get into small devices that are battery powered, it's 100% super critical. So what it means is if you look at running a neural network on, let's say, an updated DSP that's got some additional extra functions in it, or a general purpose processor or something like that, for kind of our second generation device, we get 30 times the throughput per clock just because it's super optimized, and about 100 times the energy efficiency for a comparable process-to-process comparison. So in these devices, the MCU grade, very small battery-powered devices, that's where really the rubber meets the road on the processing architecture. The other thing I think is that compared to sort of GPUs, which are the server-side universe, our processors do batch size 1 inference, which means basically 1 inference at a time, and get maximum performance. That's not true of a GPU. So that is also critical when you're doing physical world interface, because you're not bringing workloads from dozens and dozens of hundreds of millions of users together into a processor. You just have the one. So those are kind of the areas that we focused on in the processing architecture to get the most out of the electronics, most out of the energy, and deliver it to these specific types of outcomes directly.
So when we started, the first network we built was a fully connected network.
Yes.
And then we progressed to convolutions, to recurrence, and now we're doing about in transformers. Could you tell me a little bit about those changes and the benefits it brings to the industry, to our customers, to our own efforts?
As you said, our first generation processor was focused on just more or less running dense layers, and we had success with audio classification with that device. Second generation, we were much more focused on two things. One, bringing all of the other layer types to allow our own models to run better, but also the ability for customers to bring all of their networks without constraint. So for example, in audio enhancement algorithms, which are regression type networks, recurrent layers are fairly magical, and that's what's widely deployed today. In terms of classification for vision, the convolutions, and a wide range of different structures of those to get the most out of the computation are what's good there. And I think in the terminal side, the attention layers that come from all of this generative AI is we're just starting to work with it, frankly, right? You can see clearly that they also have magic properties in server scale. And I think we'll find the same types of benefits once we start working with the more edge-oriented models. And we do have models right now that run on other people's hardware, not on Syntiant hardware, that use transformer architectures to give high performance constrained speech assistance and stuff like that. So basically all of those modeling tools are just getting more and more out of the available data and allowing us to train towards more compelling and interesting behaviors and outcomes.
I think it really boils down to the models when I think about the success that we've had. I in our first year of founding Syntiant, I was thinking we were building a chip company. And when I told my friends that we're starting a new chip company, they really said that we really should start a software company. That's where the money is. It turns out we did start a software company, and I think that one of the things that allowed us to really be successful is when you came to me and you said, "Look, we need to build models, because if we didn't build models, we could only sell chips to like the hyperscalers.
Yes.
But if we wanted to sell AI chips to everyone,
Yes.
we needed to have the software."
So models have been the critical thing in terms of delivering a merchantable solution to our customers. Okay, so that as you said, the key is there are very few people who can develop well-performing edge models. Okay, almost none, but there's a huge demand for it. Okay, you look at all these devices, these terminal devices, they're interfacing with the physical world. So that creates an opportunity for a merchant-oriented solution, just like with chips. Okay, everybody could build their own chips, but the fact is, if you look at them, a lot of the models that we provide are substrates for a system, which means you build more on top of it, and they're a set of common things. So with our modeling platform, that allows them to not take we probably had 10 years worth of development on each of our sound and sight pipelines of a dozen engineers. So lowering that barrier for experienced modeling practitioners to deploy edge models, I think, is the other critical thing looking forward. But so far, definitely the models have been essential to actually getting products in the market.
So we recently acquired the Knowles consumer MEMS microphone business, and that allowed us to go from the sensor to the processor to the software.
Yes.
How do you see that accelerating the AI business?
When you have the sensors and the processing and the models, there's lots of things that you can do differently that leads to a virtuous cycle in terms of improving the whole technology platform, which will unlock a lot more applications than what we see today. And then, before you know it, deep learning interface will be ubiquitous.
It's very exciting.
It is extremely exciting.
So Steph, thank you very much for the last 7-8 years. It's been a great adventure. I look forward
Likewise.
to the next 7-8 years.
Definitely. Thank you.